G'day viewers. In this segment we'll talk about how routers forward packets. So as we get into our topic, I do want to remind you of the distinction between routing and forwarding. Forwarding is the process of handling a packet when it arrives, sending it on its merry way. Routing is the process of computing all of the paths through the network so that you'll be prepared later on to forward packets because you'll know which way to send them when they arrive. Now, we're just looking at forwarding right now, and really I would also flag that we're going to be looking at how IP does forwarding. So this is really learning about IP rather than the more general topic. As for routing, we'll get to that much later. So for now, just suspend disbelief and imagine that routers have all worked out the paths through the network, and we're just looking at how routers actually handle packets when they arrive. Before we get into the meat of that topic, let me just recap where we were at in the network layer. We really had several goals for our network layer to go beyond what we could do in the link layer with simple switch networks. We wanted to be able to scale to large networks. That's what we're getting to in this video right now, seeing how we use the hierarchical structure of addresses to scale. We also wanted to do other things, support diverse technologies. I've talked about internetworking, I'll talk a little more about that later. And we also want to use the bandwidth of the different links in the network well. This is covered by different routing formulations, and we'll get to that much later. So, let's look at how we scale to large addresses with IP forwarding. Well, without much ado, I'll simply tell you that we use IP prefixes to our advantage to achieve scaling. And here's how it works. The key observation here is that all of the IP addresses on one network belong to the same prefix. That means that in our forwarding table, what we can do is simply put down one entry for the entire prefix. And that way, if we encounter any packets that are destined to IP addresses within that prefix, we'll all send them to the same place, whichever way we should go for the prefix. Here's an example of that, and you can see here is a forwarding table for a particular router here, this router here. And the forwarding table only has a couple of entries, but they're prefix entries. So the first prefix here, that's a /18, and the second prefix is a /22. There are different next hops, so there are different things you do with addresses in each of these prefixes. But both of these prefixes could cover a relatively large number of addresses, many different destination addresses that different nodes were sending packets to. So even though there might be a large number of IP addresses represented here, and you can work that out from the prefix lengths, we'll get to that in just a minute actually, you can see that the forwarding table is quite small. It scales well. Now, it's not quite as simple as I'm making out for IP forwarding, and the reason is this, that prefixes in the table can overlap. If you just imagine a very basic notion historically with classful addresses, the blocks didn't overlap. But with prefixes, you can have prefixes of different lengths and they can overlap one another. To resolve this, we use a forwarding rule called the longest matching prefix rule, which I'll tell you about. And this rule is able to combine the hierarchy that we get from using prefixes with a little bit more flexibility, even though the longest matching prefix rule is a little more complicated than a straightforward table lookup. The rule is simply this. For each packet that you're trying to forward, you look at its destination and you find the longest prefix entry in the table that contains the destination address. That is going to be the most specific entry. This is why it's called the longest matching prefix, of course. So we might find in our forwarding table that that the destination address fits within several different prefixes we have. We want the most specific of those. And then we'll simply forward the packet according to the rules for the next top router for that most specific prefix. That sounds pretty simple. Let's work through an example just to see how these prefixes can overlap and what it means. So here's the same table from before with the address ranges, and I'm going to show them on this figure. Here, IP addresses go up from all 0 at the bottom to 255.255.255.255 at the top. So let's put some of the addresses on here and show where the ranges are. Okay, so this first prefix here, the bottom address is 192.24.0.0. That's down here. That's the lowest address, and so I just drew that in here. The next prefix in the table, its bottom address is 192.24.12.0, so it's higher, and I've drawn that here. We don't have the top addresses yet. Let's try and calculate them. Okay, so for the /22 prefix, that fixes the top 22 bits, leaves the bottom 10 bits free. So we will calculate the top address by taking 192.24.12.0 and turning on the bottom 10 bits. Well, if I do that, I'm going to turn on the bottom 8 bits for sure. That gives me the 255 up here. And I'm also going to turn on the bottom 2 bits of the next one. That's equivalent to adding 3. So we go from 12 to 15. And I end up with 192.24.15.255. So you can see for the /22 prefix, I've colored that with the pink diagram. And I've made it longer because it's a more specific prefix. What about the top of the other one? So for this other prefix, 192.24.0.18, well, this will have 2 to the 14 addresses in it. The last 14 bits are going to be free. So I've got to turn on the last 14 bits. So what will I get when I do that? Well, I started from all zeros and I turn on the last 8, I get 255. Then I've got to turn on another 6. So it's going to be 0, 0 and then all ones, and then 6 ones. If you convert that from binary to decimal, you should get 63. So the top address will be 192.24.63.255. This is the grey block where we forward to D. This is a much bigger block. And the other pink block is within it. And I've drawn this to be not as wide because it's a less specific address. Well, anyhow, this is a representation of our forwarding table. Let's try and use it for forwarding now. So I have several addresses here. Number 1, number 2, and number 3. Let's see where they go. The first one, number 1, 192.24.6.0. Well, where is this on our address range? Well, it's somewhere in here because it's below 12.0. So this is number 1. So guess what I want to do to forward number 1? It's in this grey region here, so I'm going to forward it to D. Okay, what about let's do the last one. What about number 3? 192.24.54.0. Where is that? Well, it's above .15.0 and it's below 63.0, so it's going to be in here somewhere. Number 3. So number 3 is also going to go to D. Okay, the middle one, well, you can probably guess what's going on here. It has a .14.32, so that's actually somewhere between the lower and higher address of B, so it's going to be in here. Number 2. Number 3 was in here somewhere. So this one will go to B. So you can see how we use the forwarding table to do this, and this is the longest matching prefix algorithm. Okay, so there's one other thing I can tell you about routing and forwarding, and how we scale it using a little bit of hierarchy and so forth. There's actually a distinction in the internet between hosts and routers. So in the internet in particular, routers do the routing, so hosts don't do the routing. Hosts just send packets to routers. That may sound a little obvious, but that's actually a little bit of a choice. In particular, what I'm trying to say here is we place the responsibility of knowing which way to send packets for all IP addresses on routers. They need to do the routing, so they'll be able to forward to all different destinations. Hosts, on the other hand, are on a local network, so they might be able to reach hosts on their own prefix, but they send any remote traffic that's off the prefix to the nearest router. So hosts really don't need to participate in routing, they just need to know the nearest router. And you can see here, the host is saying, okay, if it's a local, I'll send it on my network, but if it's not, just send it to the router, because the router will have to work out which way to go, and it might be different ways for all sorts of different IP addresses. The reason that I'm bringing this up now is that this distinction between hosts and routers fits very naturally into our longest matching prefix rule. In particular, we can formulate a forwarding table for hosts which has this kind of behavior. And we just use it by using a default route to 0.0.0.0/0. That might sound a little odd, but a forwarding table for a host will look something like this. It will have the network prefix that the host is on, so a host will need to learn that. And if you're sending to a destination in that address, it's to a local host, so you just send direct to that next host because it's on the local network. Then we have this funny entry here, 0.0.0.0/0. Well, what is this? Let's think about it. It's a 0 length prefix. That means that the remaining 32 bits, that's everything, can be free. So this is really an address meaning everything, all IP addresses. is encoded simply using a prefix notation. And the next stop for that is just send to the router. So that way we'll let the router worry about it. So our longest matching prefix rule allows us to encode this fairly simply and directly. And you can see here what I'm getting at is the flexibility of the longest matching prefix rule. In particular, we can use longest matching prefixes in a couple of different ways. We can add less specific entries to a forwarding table to provide a kind of default behavior. You saw that with hosts, send it to the router. But we might also use it for routers within a network. For instance, you might have an enterprise network and routers in it might know which way to go for all sorts of your different networks. But for other IP addresses which are outside of your network, you might have a default rule saying send it to your ISP router. And your router could simply use the default rule to get packets out of the network. Similarly, instead of providing defaults, we can also provide special case behavior. You might take up particular addresses and request by using a more specific prefix that they get special handling at a router and they be sent a different way than they would normally. This might be for reasons of performance. Maybe this is a voice over IP call and you want to route it over a low latency path. Or it might be for reasons of security. This might be suspicious looking traffic and you want to send it along a path to a special box to inspect all of the packets more carefully and see if there's a security problem. This could be for any number of network management reasons you might like to come up with. The point is that we get a certain degree of flexibility from this longest matching prefix rule and we can use it to our advantage when managing networks. Well, the flip side of this is to talk about the performance of the algorithm. How well does longest matching prefix perform? Well, in terms of table size, it performs very well. We use hierarchy to get a nice compact table. And by using prefixes of different sizes, we can actually get quite a compact table. Note that this depends on people using addresses which have a reasonable prefix length, or actually rather small prefixes, which contain a large number of addresses, so less specific prefixes. Good grief, that's all I'm trying to say here. Actually, if everyone uses very specific, more specific addresses, we won't get as much compaction as otherwise. And another aspect of performance is just how fast the lookup operation runs at routers. It turns out that the longest matching prefix rule is computationally more complex than a simple table lookup. Actually, it can be quite so in some cases with strange overlapping entries. This was a concern when we were trying to build routers in the early days and make them fast. Today it's not really a performance concern. You can just get silicon which will do this and you don't need to worry about it. So I wouldn't worry about it too much if I were you. And finally, I've really just talked about addresses for forwarding. I do want to point out that it's not all about addresses. Here's our picture of an IP header again, and you can see the addresses were in here, but I've shaded in pink everything else in the header, and there are a lot of other fields. What do all of those other fields have to do with forwarding? Well, there are many other small aspects of forwarding. We've touched on some. Well, actually, I'll tell you about others in the future. And let me just briefly mention a few. You might have noticed there's a TTL field here, a time to live field. This value is decremented as you go through routers so that if it hits 0, you can throw away the packet. The reason for this is to protect against routing loops. What if there's a mistake and packets are going round and round in a circle? They can do this very fast and clog up the network. There were also other fields there, such as a checksum. A header checksum is used to just check that the header values are all okay to provide a little bit of added reliability. There are fields in there for fragmenting large packets. If the packet is too large to send it to the next link, we're going to break it into pieces. We'll cover some of this in a segment that's coming up. There are other fields in there to be able to deal with congestion. The network may be congested, and these other fields help us to send congestion signals to hosts. And there's other functionality to be able to generate error messages that goes hand in hand with IP. This is ICMP that will help us manage the network. We'll get to that later. And there are even other various optional fields which I'm not going to cover in any of these videos. If you're interested in all of this, you can look in your text for more information, a little more about IP. But we will get to some of the more important aspects quite soon.